Okay, so let's take a look at sort of these trig functions in action with a couple more examples of different types. First of all, let's suppose that I just give you this triangle. It's a right triangle. It's a good start. And this side is 2, this side is 4, and this here is the angle theta. And let's find all the trig functions for this angle. So I want to find sine, cosine, tangent. Let's even find cosecant, secant, and cotangent for this angle. Well, it looks like a tangent won't be a big deal because that's just opposite over adjacent. So that's going to be pretty good. But what about sine and cosine? I need to know the length of the hypotenuse. I don't know what that is. That wasn't given to us. Well, can we find it? Sure, we'll just use Pythagorean theorem. So using the Pythagorean theorem, what I have is the following. Just redrawing that picture. This is 2, this is 4. I don't know what this is. I'll just call it h for hypotenuse. I know that this squared plus that squared has to equal the hypotenuse squared. So the hypotenuse squared has to equal, well, 4 squared, which is 16, plus 2 squared, which is 4. So therefore, h squared has to equal 20. So I could take plus or minus the square root. Here I can get rid of the minus square root because remember, this hypotenuse is a length. Length is always positive. So here I can dismiss the negative square root as a extraneous root. And I would see that h equals the square root of 20. Now that's fine by itself, or you could realize that the square root of 20 is just 4 multiplied by 5. And by laws of exponents, I could just take the square root of each of those terms, square root of 4 times square root of 5. And the square root of 4 is 2. So this is just 2 square root of 5. So knowing two sides of a right triangle, I can actually find the third side. In fact, that would have to be 2 square root of 5. Great. Well, now I can just rip through all the trig functions. So sine of theta, that's opposite 4 over hypotenuse, 2 square root of 5. So I can cancel a little bit and see just 2 on top over the square root of 5. What about cosine theta? Well, that's adjacent over hypotenuse, which is just 1 over the square root of 5 after you cancel. Tangent would be opposite over adjacent, 4 over 2, which is just 2. And what about the reciprocal ones? So let's do cosecant. So cosecant, remember, is just the reciprocal of sine of theta. So I just flip this, and I see square root of 5 over 2. Secant is just the flip of cosine, so that's just the square root of 5 over 1. And cotangent, the only one that's sort of easy to remember, is the reciprocal of 2, which would be a half. So in fact, there's all the trig functions. Just knowing two sides, I was able to find all the trig functions of this angle. Let's try a different type of question. Suppose that I tell you that theta is some acute angle, so it's between 0 and 90, and that the sine of theta equals 12 over 13. I want you to find all the other trig functions for that same angle. Well, how in the world can we possibly find all the other trig functions for that angle that we know is acute, just knowing its sine? It seems impossible. Until we start thinking about, since this thing is acute, we could think about it as being one of the angles in a right triangle. So let's just draw a picture. So if we draw a picture, and pick an angle to be the angle theta, let's say this one right here. Doesn't make a difference which one. You can't pick it to be the 90-degree one, but you could pick it to be either of these two. Suppose I say it's that one. Well, if the sine of theta equals 12 over 13, that means I could take my triangle so that the proportions of, now what's sine? It's opposite over hypotenuse, would be in that ratio. So opposite, so I could say this thing has length 12, and that forces this to have length 13. Hey, well, this is the thing I just did. If I know two sides, I can find the third side of a right triangle using Pythagorean theorem. So how would Pythagorean theorem look here? Now I want to find this length. That's a leg. Let me call it L for leg. It's not the hypotenuse. And so what do I know? I know that this squared plus that squared should equal that squared. So that means that L squared plus 12 squared, which is 144, should equal 13 squared, which is 169. So that means that L squared should equal, if you bring this over, 25. So I take square roots, but I got to take plus or minus square roots. I can always get two answers. But in this case, I can just take the positive one because this is a length. And the square root of 25 is just 5. So in fact, this length must be 5. Well, great. Well, now I can, in fact, read off all the other trig functions, right? I already know sine, opposite over hypotenuse. What's cosine? Cosine is adjacent over hypotenuse, so that would be 5 over 13. What's tangent? That would be opposite over adjacent, so 12 over 5. What would be cosecant? Well, that's just the reciprocal of sine, so that would be 13 over 12. Secant would just be the flip of cosine, so 13 over 5. And let's see, cotangent would be the flip of tangent, which would be 5 over 12. So that's pretty cool. Just knowing the value of an acute angle, I can find the sine of the value of an acute angle. I can find all the other trig functions because I can actually reconstruct a triangle that has that as its sine and then read off all the other ratios. Pretty cool. Okay, up next we're going to take a look at more connections sort of between triangles and angles and actually seeing how we can take the angle of something, the trig function of something, and correspond it with its triangle and start to get information back and forth about each of those things. We're just sort of getting our feet wet here on this trig stuff, but the idea is to build up some intuition, to see connections with the geometry and the trigonometry here, and then to start to also find out the values, the trig functions, of certain special angles. We'll use those later. So anyway, a lot's going on here, and it's all trig. Fun. I'll see you soon.